ancient civilizations have felt the need to study the sky. Their observations were restricted by the capabilities provided by the sole optical instrument they possessed, the human eye. All they could see, without being able to understand their nature, were 3,500 stars at most. But today, science has managed to observe the universe at enormous distances of up to almost 13 billion light years. 1 light year is the distance a light ray travels in a year and is about 10 trillion kilometers. The modern image of the universe reveals a huge, complex, and impressive environment, whereas we exist and evolve on the surface of a small but hospitable planet called the Earth. Earth is the only oasis of life, at least on our solar system. The conditions prevailing on its surface allow the existence of huge amounts of water in liquid form, both in the seas and on land. Water in liquid form is the most essential ingredient for the formation and development of the phenomenon of life. Limited to the environment of our planet, we have so far been able to visit and explore only the very near celestial bodies, such as the Moon and the planets of our solar system. But how did we manage to study the universe at such enormous distances and understand its content, its structure, and its evolution? How did we unveil many of its secrets? Unfortunately, only few people know that all this knowledge is gained by the collection and analysis of the dim starlight that reaches the Earth from those remote heavenly bodies known as stars. This adventure actually began in 1609, when the Italian scientist Galileo Galilei turned a small homemade telescope to the sky. His observations opened a huge window to the universe and revealed its greatness. The optical telescope operates in the same way as the human eye. The telescope collects light and focuses it on a single spot. There are refracting telescopes, which employ lenses, and reflecting telescopes, which use concave mirrors to collect and focus the light. The amount of the collected light depends on the area of lens or the mirror of the telescope. A large optical system collects more light and thus makes visible dim celestial objects which are invisible to the human eye. Most dim objects are invisible. In other words, a telescope is a kind of time machine that allows us to observe the universe as it was in the past and thus understand its evolution. As time passed, the telescope evolved from Galileo's simplistic instrument into huge, technologically advanced and precise scientific instruments. Today, we use large optical telescopes placed strategically on remote mountaintops all over our planet. Far from urban areas, they avoid light pollution, which prevents astronomical observations. Furthermore, in the high altitudes on mountains where they are built, the atmosphere is much more transparent and stable. The larger telescopes in the 8 to 10 meter range aperture that are used by the American astronomers placed on Mauna Kea in Hawaii. The European Southern Observatory has erected the Very Large Telescope, VLT, on Cerro Paranal in the Chilean Atacama Desert. This telescope consists of 4 reflectors with a diameter of 8.2 meters each. The Atacama Desert is one of the most arid places on Earth, thus providing ideal conditions for astronomical observations. These telescopes can observe in optical and infrared radiation and can record objects 4 billion times dimmer than those that can be observed by the naked eye. They weigh hundreds of tons, but are capable of pointing and tracking celestial objects with extreme accuracy. They also employ adaptive optics, which can compensate for atmospheric disturbances. And are equipped with many auxiliary instruments such as light-sensitive cameras and high-technology spectrographs. These large telescopes are mostly used for the study of large-scale structure and the evolution of the universe by observing the remote clusters of galaxies and the interaction between their members. Alongside these giant telescopes, the older and smaller telescopes continue to contribute significantly in scientific research. In the near future, new giant Earth-based optical telescopes such as the European Extremely Large Telescope ELT will be available to astronomers. It will have a 40-meter diameter segmented mirror and will be erected at Cerro Armazoras in the Atacama Desert in a few years. Yet, in spite of all these technological advancements, we still cannot eliminate all the problems caused to astronomical observation by the Earth's atmosphere. Thus, we had to put telescopes in space. Since 1991, Hubble observes the universe with unprecedented accuracy and is credited with many important discoveries. Hubble's successor is the James Webb Space Telescope. This telescope has a 6.5-meter mirror and is designed to observe light in infrared radiation. It will be able to observe galaxies at a distance of 12.5 billion light years.
One main role of the optical telescope that we know is the study of the individual celestial objects. So we take images of these objects, and a relevant example is the images of the Hubble Space Telescope that have become famous. But the astronomical object in general emit not only in the visible band that is accessible to optical telescopes, but they emit radiation throughout the full electromagnetic spectrum.
But light is something more than that recorded by all mentioned optical telescopes. Light consists of electromagnetic radiations at different frequencies. All these together make up the electromagnetic spectrum. Most of them, of course, invisible to the human eye, but also to even the most advanced optical telescopes.
Optical light, that is the light we observe with our own eyes and optical telescopes, played a most important role through the centuries in helping us to understand how the universe works. Through optical light, we could study the motion of the planets on the night sky and observe the birth and death of stars. However, many decades ago, we realized that the optical light is not the only radiation that exists in the universe. We discovered the X-ray radiation, the radio waves, and the infrared light. All these comprise what is known as the electromagnetic spectrum. The stars and the galaxies emit only a tiny amount of their energy in optical light. They emit also powerful radiations such as X-rays and gamma rays, which come from places in the universe with the highest temperatures, with millions of degrees temperature, such as the matter that falls into giant black holes in the centers of distant galaxies. We need to observe all these types of radiation, from X-rays to radio waves, in order to form a complete picture of the astronomical objects we observe.
The celestial bodies we observe and all astronomical phenomena emit in several frequencies simultaneously, but they emit most strongly in some frequencies according to their energy level. These hot and violent processes radiate mostly in short wavelengths, whereas the colder and quieter processes radiate in longer wavelengths, such as microwaves and radio waves. Radio waves are observed with giant parabolic antennas called radio telescopes. These instruments can observe the sky 24 hours a day, regardless of atmospheric conditions. There are many radio telescopes carefully placed all over our planet. The most sophisticated of them is ALMA, which is situated on a high-altitude plateau in the Atacama Desert in Chile.
The atmosphere of the Earth contains atoms of oxygen and nitrogen, and they absorb the X and gamma radiation through a process which is called photoelectric absorption. The high energy of these radiations goes into removing electrons from these atoms. Although the atoms in the atmosphere are well spaced, the total number of atoms that the X and gamma radiation encounter is very large, taking into account the total thickness of the atmosphere. This makes almost impossible that the X-rays and gamma rays coming from astronomical sources reach the Earth's surface. This is good for humans, but bad for astronomy. So finally, we have to put the telescopes in satellites.
Most of the electromagnetic radiation cannot pass through the Earth's atmosphere. For this reason, we put in orbit space observatories that can observe in all the frequencies of the electromagnetic spectrum. Most notably, the high-energy ultraviolet, X-rays and gamma rays cannot be observed from the Earth's surface at all. The only way to observe the universe at high energies is to use observatories in space. These observatories allow us to study physical processes previously unimaginable. But X-rays and gamma rays allow us to observe the most violent and impressive phenomena of the universe. For example, the sky seen at these wavelengths is completely different from the usual image of the quiet night sky.
When astronomers refer to the most energetic astronomical phenomena in the universe, we are basically referring to black holes of all sizes, supernovae, kilonovae, gamma ray bursts, and neutron stars, as well as hot gas in galaxy clusters and in the circumgalactic medium. In those places of the universe, the matter is under extreme conditions, violent collisions, powerful explosions, fast rotations, or strong magnetic fields. There, particles are accelerated to relativistic energies, and matter is heated to tens and hundreds of millions of degrees. These high temperatures are responsible for the production of radiation, mainly in the X-ray and gamma ray bands. Keep in mind that temperature is a key to producing different types of light.
But light is not the only source of information about the physical processes in the universe. During the violent, high-energy natural processes in the universe, elementary particles called neutrinos are produced in inconceivably large numbers. Neutrinos are elusive particles that move at relativistic speeds, have minimal mass, and rarely interact with the rest of matter. To detect them, we use special sensors deep in the ground or at sea to minimize the various interferences. Finally, as the general theory of relativity predicts, the space-time web is altered by the existence of mass and energy. Some of the most violent and energetic processes in the universe produce ripples, the gravitational waves in the fabric of space-time. These cosmic ripples travel at the speed of light, carrying with them information about their origins as well as clues to the nature of gravity itself.
The first observational evidence of the existence of gravitational waves came from a study of a binary system of pulsar. Hughes and Taylor discovered that the orbital decay of this binary pulsar is perfectly consistent with the emission of gravitational waves as predicted by Einstein. Later, in 2015, we observed for the first time by Earth gravitational waves. The LIGO interferometers observed the 14th of September 2015 a signal coming from the merger of a binary system of black hole. This opened a new exploration of the universe through gravitational waves.
Recently, we have managed to develop special observatories for recording these ripples as they pass through our planet. LIGO, the Laser Interferometer Gravitational Wave Observatory in the US, and the Virgo antenna, hosted at the European Gravitational Observatory, EGO, at Pisa, Italy, employ very sensitive laser interferometers to detect them.
Multi-messenger physics, as we do in AHEAD 2020, which means we try to understand the universe not only through light, but also through particles, neutrinos for instance, high-energy photons. And if you take the gravitational waves, the gravitational wave antennas, we say that we listen because the frequencies that we measure are frequencies of the acoustic range. We don't listen the sound, the frequencies we measure are acoustic frequencies. So this gives us, let's say, inspires us to think of understanding the universe not only through light, but through multisensorial practices, that is, not only light, but sound and even particles.
Let's have a look at some of the most violent phenomena in the universe that must be observed by all our instruments in order to have a clear picture of the underlying natural processes. The most massive stars suffer violent death during supernova explosions. After these explosions, the cores of stars can end up as white dwarfs, neutron stars, or black holes. In particular, the stars with high masses end up as what we call black holes. From these stellar remnants, nothing can escape. Even light gets trapped, making these objects invisible. Black holes attract everything that goes near them, thus increasing their mass. Matter, as it collapses onto black holes, creates an accretion disk around them as it spirals inward. In this disk, the temperature and kinetic energy are so high that the gamma rays and X-rays are generated. At the same time, strong gravitational fields create jets which move with a speed close to the speed of light and interact violently with the interstellar matter that surrounds them. This produces radiation at all light frequencies. The death of medium mass stars creates what we call neutron stars. These small but very dense objects spin at very high velocities, and their radiation can most easily be observed when the beam of emission is pointing toward Earth. This creates periodical changes in their luminosities, and this is why we call them pulsars. Pulsars may also have accretion disks and jets, but their scales are smaller compared to black holes. Binary stars can be very close together, interacting strongly with each other, or eventually merging. There are special cases when one of the binary stars is very dense, like the results of the merging of two common stars or the more violent merging of two neutron stars. These mergers always end up in the brightest explosions known, which produce copious amounts of X-rays and gamma rays, the gamma ray bursts. Waves. Less often, but at larger scales and more impressive, are the mergers of two black holes. These are the most violent phenomena in the universe and generate inconceivable amounts of energy in the form of gravitational waves. The environment at the center of our galaxy is a supermassive black hole which interacts with surrounding matter. Studies of the motion of nearby stars revealed that the mass of this black hole is 4 million times the mass of our Sun. Observations from the Fermi telescope showed that there are two large lobes of gamma rays that expand out to 25,000 light years from the center of our galaxy. These lobes are ejected by violent phenomena at the very center of our galaxy. Galaxies that emit huge amounts of energy from their nuclei are known as active galactic nuclei, radio galaxies, quasars, and blazars. These galaxies have supermassive black holes in their centers with masses 1 million or even 1 billion times the mass of our Sun, and accrete huge amounts of matter and jets that extend out into the intergalactic medium. The interactions, collisions, and mergers of whole galaxies play a crucial role in their evolution.
We have come a long way to understand our universe. However, there are a very long list of open questions that we need to answer. High-energy astrophysics will play a fundamental role in understanding how the universe works and solving some of the most puzzling issues that we are faced today. A few of them are related to the early universe, when the first stars formed, when the first metals were produced, the metals that actually find their way in the universe and throughout eventually coming into our bodies. Also the role of black holes that were formed in the early universe and how they shape the life of all the galaxies, including our own. It's an open question. In this regard, the Athena Observatory, the large X-ray telescope that is being developed by the European Space Agency, will provide answers to these questions.
The decoding of the hidden messages that the light of stars carry, as well as the torrents of exotic particles and space itself, reveal to us the universe in all its grandeur. Humans, although bound on the surface of a small planet called Earth, have the ability with science to glimpse the limits of the visible and invisible universe.